Very good morning to all the students present in today's lecture of digital communication. We have discussed digital carrier modulation techniques till last lecture, and today we are going to start a very interesting topic of noise. What is the presence of noise in communication system and what is its uh, characteristics? I hope my voice is properly audible. Okay.
Yes, sir.
Okay, thank you. Let me share my screen. Just a moment. Is the screen visible?
Yes, sir.
Okay, thank you. So today we are going to see uh, what is noise in communication system and its presence, what impact it has over the performance of the communication system. So noise in communication systems. So there are various aspects of noise. There are different types of noise we are going to discuss and what impact they make when it comes to your noise representation across the entire bandwidth we are going to see. So if you look at this, noise means you have transmitted some signal. When you refer to noise, essentially you refer it with taking example of the received signal. So signal at the receiver side, you observe there is some corruption which is happening in the received signal. Now that corruption or the received signal gets corrupted because of two things, because of the channel characteristics itself, and another is the front end system of the receiver, front end systems of receiver means the you can say the receiver electronics, the front end receiver electronics or the circuits, they introduce some noise. We all know noise is undesired signal. So essentially noise is almost random when it comes to your communication system, but many a times if you are able to model the channel noise, you can get rid of it. In a sense, it becomes deterministic. For example, if there is a noise of power supply hum, okay, power supply hum which is occurring at 50 hertz, so we can make use of filters we call as notch filters. I hope you might have heard of notch filters, which are removing specific frequency values or components at particular frequencies. So though it is majorly random, but we can get rid of it by understanding the noise, by understanding the power spectral density of the noise. So we need to design special filters for that to get rid of noise. And generally in communication system, noise is of a very large bandwidth. With reference to communication system, BW means bandwidth, I mean large bandwidth presence. Okay. Now if you look at the classification of noise, so you have two categories: externally generated and internally generated. Okay, under externally generated, what are the different types of noises you can have, or the system can have? Atmospheric noise, then you can have extraterrestrial, and man-made noises. So these are types of externally generated noises. So we will look at each of these categories, both in externally and internally generated. What is their frequency, presence, etc. In internally generated, we are referring to thermal noise, then short noise, okay, and last is your partition noise. Okay. So this is a broad classification of the noise sources and its classification. Fine. So we start with these externally generated, and if you look at the atmospheric noise first, atmospheric noise. So when we talk of atmosphere, essentially we are referring to the lightning discharges, thunderstorms, etc. Okay, so atmospheric noise, you think of lightning discharges. Lightning discharges will definitely occur when thunderstorms and this tornado and all will be there. Okay, the equivalent noise current is very high. It is of the order of thousands of ampere when the discharge is there. That much high magnitude. Generally, it is broad spectrum, means it covers from very low frequencies till hundreds of megahertz. Okay, very low to hundreds of megahertz. Now, even if you divide further this spectrum and you compare its impact, you will find a lot of literature they are referring. It is the impact is severer, and the highest degree of impact is in medium wave band. Highest impact in medium MW, I'm writing medium wave band, which is 526.5 till 1600 kilohertz, and in comparison to short wave band, relatively short wave band, which is 3 to 25 megahertz. Okay, so just to remember this, you know. And it is least impact for, yesterday we have seen VHF, UHF range. So it is least in this case, and it is good thing, right? So 30 to 300 megahertz is what is our VHF. UHF is 300 to 3000 megahertz or 3 gigahertz, right? So good thing. Majority of communication, wireless communication, is happening in this range. Okay. Next is your extraterrestrial noise. So extraterrestrial definitely is referring to galaxy, solar noise, etc. So predominantly it is the solar noise and galactic noise, means noise in the galaxy, in the space. So when you look at solar, so solar storms, you might have heard, that there is a solar storm and it is going to impact a lot of news, coming every year because of solar storm. The communication system, satellite communication system, they are going to be affected like that. We used to hear this. Um, so what happens is, sun is a gaseous body, right, with temperature, surface temperature of around 6000 degree centigrade. So because of so much high temperature, it radiates huge amount of noise. Okay, so there is a cycle we call it 11-year cycle. 11-year cycle. So every 11 year we have a sunspot, and it's also known as sunspot cycle, right? So every 11 year there is significant uh, dissipation of noise. Okay, because of the this very high temperature at the surface, because of lots of things happening at the surface of sun. So that is very challenging situation for the communication system which are there in our outside space or maybe in the orbit. Galactic noise, if you look, galactic noise, it is because of other stars. Solar is from our star and galactic noise is because of the other stars. Definitely if it is from other stars, it will be less than solar. Other stars, they are far away, right? But not so less that they are insignificant. So less than solar, but not insignificant. Okay. Now the galactic noise range is starting from few megahertz till few gigahertz. Okay. Now this is the presence in the outside, our outside Earth system, right? But when we look at Earth, so there are a lot of layers, right? Layers in our atmosphere. What is the role of those noise layers in mitigating effects of these galactic noise? So if you look at ionosphere, so the components in this few megahertz to few gigahertz, which are greater than 20 megahertz, components, these galactic noise components, which are greater than 20 megahertz, they only pass through ionosphere. Because of the nature of this layer. Components which are greater than 1.5 gigahertz, they are essentially absorbed by the hydrogen, which is hydrogen which is floating in the space, in the interstellar space. So components which are greater than 20 megahertz, they only pass through ionosphere, and components which are greater than 1.5 gigahertz get absorbed by hydrogen in interstellar space. Okay, so the effective sorry so the effective frequency range for the extraterrestrial noise to have an impact on Earth systems is 20 megahertz to 1.5 gigahertz. That is the nature of your extraterrestrial noise. Are we good, students?
Yes, sir.
Okay. Next is your man-made noise. So man-made noise, we all know a lot of man-made, thousands of systems are there generating noise. Biggest is your automobile ignition, okay, and aircraft ignition. Then you have fluorescent lamps. They are also source of noise. Then you have sparks in motors, electric motors, etc. So lots of sources are there, but generally it is of the range 1 megahertz till 500 megahertz. And with man-made noise, when because of these activities being more into urban area in comparison to rural areas, more urban presence is there for man-made noise. So it has got more urban presence for obvious reasons. So this is about all about externally generated noise. Next is your internally generated, and first we are looking at thermal noise. Have you ever heard of thermal noise? Ever? Never? It's okay. No issues. So what is thermal noise? So since it is under internally generated, so you have to think of the material which are there in the system, in the circuits or in the devices. So at any temperature above 0 degree Kelvin, the free electrons which are there in the conductor, what happen? They possess some kinetic energy. Okay, and because of this kinetic energy which they are possessing, they are in some random motion. Now uh, they will be in random motion. They will have collisions with the lattice. I hope you all know what is a lattice. Lattice is the structure, okay, geometry. They are in geometrical arrangement of uh, the the atoms, molecules of the material which are there. So because of some temperature above 0 degree Kelvin, the free electrons in conductor, they possess some random motion, and because of this motion, collisions occur in the lattice. So this random motion of the electrons is actually generating this random motion is resulting into a generation of random current flow within the conductor, okay, and creating a random voltage across it within the. So it is something which you cannot prevent. It will be there, right? There is nothing we can do about thermal noise. We have to bear with it. Generating a random voltage. Okay. This thermal noise is also known as Johnson noise. So if you look at the general formula for the power spectral density of thermal noise, means its characteristic. So you have to consider a temperature of capital T degree Kelvin. So at a temperature of capital T degree Kelvin, the power spectral density PSD of thermal noise across a conductor having a resistance capital R ohms is given by this formula. Beta F or del F, many books they refer to del F, beta F also you can refer to. This formula is given by 2 into R H F E H and F upon KT. So this is actually to the power E to the power HF upon KT minus 1. The unit is volt square per hertz. What is H here? H is the Planck's constant. What is the value of Planck's constant? 6.6 into 10 to the power minus 34 joule second. Okay. So where H is your Planck's constant joule second. K is Boltzmann constant, which is 1.38 into 10 to the power minus 23 joule per Kelvin. So this is the formula for PSD, power spectral density of the thermal noise. So F definitely is referring to the frequency. So we see that this power of the noise, is inversely proportional to F. So if you find the maximum value of the noise power, noise strength, it will come. So we need not to derive it, just remember this formula. Maximum strength for noise at F equal to 0, it will be 2 kTr volt square per hertz. But practically, when it was analyzed, this PF is constant up to PF is observed to be constant up to 10 to the power 12 or 13 hertz. So no matter if you give F here, it will come this one. PF is, so we, instead of taking PF max, we refer PF as 2 kTr volt square hertz, maximum value take. This is also known as white noise. So when you are considering the PSD or the power distribution of the noise in such a way, you're calling it as a white noise. A huge bandwidth it is having its presence, a constant presence. White means constant strength of the noise across the entire bandwidth. Okay, so if you look at the RMS value, root mean square value of voltage generated by such noise across a resistor having a resistance R, that will be 2 kTr del F volts, where del F is your bandwidth. So these all formulas you have to remember. That's it. So there is something we call as noise resistor modeling. So you can see the RMS value of voltage across a resistor R is this much. So this is the noise equivalent, the impact of noise, electrical impact of your noise. So if we model it We call it noise resistor modeling. Okay, so what does it say? If you have a R ohm which is noisy, this is equivalent to a voltage source, noisy voltage source having a PF as 2 kTR volt square per hertz, and a noiseless resistor with R ohms. So every component, every device, it is having some material which is used to construct it. So there will be thermal noise. So there will be thermal noise, and because of that thermal noise, there will be equivalent electrical representation. So if you take a simple general resistor having R ohms resistance, definitely some noise element will be there because of the thermal noise, and you separate out the voltage source and noiseless. So this R ohm is noiseless, pure, without any thermal noise. I mean, it is ideal modeling, right? Essentially, that is inherent. Are we good, students? Please speak up.
Yes, sir.
Okay. Now there is one important rule, you can say. So when you have, say, two resistors, if you are using, they are connected in series. So what will happen to the noise? Their noise power spectral density, it can be added when two resistors are connected in parallel, series. Their noise power or PST, it can be added for equivalent noise, but you cannot add the noise voltages, not the noise voltages. But when two resistors are connected in parallel, what is the rule?
1 by P1 plus 1 by P2.
Yes, so their noise PSD in ampere square hertz, not the volt square hertz. In the equivalent unit conversion, it can be added, but not their noise currents. Okay, so their noise power or PST, it can on this, it is in ampere square hertz. And now we are talking parallel, so we have to take current into account, not their noise currents. Okay. This is all about thermal noise. Next is your short noise. Thermal noise is also known as Johnson noise. And when we are taking the formula for PF equal to 2 kTR volt square per hertz, it is white noise, because to a very large bandwidth, up to 10 to the power 12 and 13 hertz, it is constant. There is no F. Okay, if you remember this PF formula, PF equal to 2 kTR, there is no F, so it is constant. So this constancy, you can say, this constant value of the noise power across a very large spectrum, we call as white noise. So you can see how different nomenclatures are there, but all are referring to thermal noise. Next is your short noise. So short noise, it is produced in vacuum and semiconductor diodes. Vacuum diodes were there already earlier. So short noise, it is produced in semiconductor diodes, photodiodes, bipolar junction transistors, etc. So if you look at vacuum tube, they electrons from the cathode, if you consider vacuum tube. Similarly, there is generation of electrons or emission of electrons in BJT from where? Emitter, right? So emitter based collector, right? So this generation of electrons from cathode in case of vacuum tube, from emitter in case of BJT, this is random in nature. I mean, there is no deterministic way to quantify the number of emitted electrons. So this is kind of random emission. Random emission of electrons. So this emission is random. So this randomness, which is there in the emission or generation of the charge carriers electrons, and we remember the diffusion of minority carriers across different junctions. We have a drift, right, of majority carriers across the junction, all these things which are related to semiconductor devices. So these all become kind of random. You cannot exactly quantify the amount of drift, the amount of the diffusion of the minority carrier. So there are two components, right? Diffusion current, drift current. I hope you remember. So we find the mean squared value of short noise current in semiconductor devices. So whenever this word comes to your mind, short noise, think of semiconductor devices. Okay. So we take mean squared value of short noise current in semiconductors is given by IN square equal to 2 IO this is I R Q into del F amp square unit, where this I is your DC current flowing through the PN junction and I naught is the reverse saturation current. So this is about the formula for the short noise. Then what is the time? I think we stop at this point and we can take it further after the evaluation, internal evaluation next week, and predominantly our unit 1 is over. So if you have any query, you can discuss, or else we are good to end this session today and start revising. You can you can contact me if you have any clarity to be given for any topic. Okay, you can drop me message if I'm not reachable. You can drop me message over Teams, and definitely I'll come back to you. So if no further query is there, thank you everyone.